Nandini,
Hello, ma'am.
you
Can you
can
hear me?
start. Yes, Nandini, you can start now.
Okay. Good afternoon to everyone. This is Nandini from ECE department. I'm here to introduce Dr. Raja Chandrasekhan sir, professor and R&D coordinator in Sri Sai Ram College of Engineering, Bangalore since April 2022. Sir has 17 years of teaching experience, which includes 6 years of post PhD as an associate professor. Earlier, Sir has worked as a faculty in reputed organizations such as Vignan University Guntur, KL University Vijayawada, MVJ College of Engineering Bangalore, Anjalai Ammol Mahalingam Engineering College, which is in Tanjavur, Velamol Institute of Technology, Chennai, King's College of Engineering, Tanjavur. Sir has obtained PhD in Information and Communication Engineering from Anna University, Chennai, MTech from Sastra University, Tanjavur, BE from Sharanath College of Engineering, Trichy. Sir has 3 SEIC and 5 Scopus indexed publications. The H index factor in Google Scholar is 7, and in Scopus it is 6, which is including 241 citations, and in Pablos it is 5, which includes 138 citations. Sir has completed 2 international level courses in Coursera in 2020 and 2021. Sir has presented guest lecture sections in Pondicherry Technology University, AICT sponsored course, and other organizations in 2021 and 22. It's my privilege to introduce Sir, and with all due respect, I would like to continue. I would like to hand over the session to you to continue for further speaking. Yeah. Thank you so much.
Yeah, thank you. Thanks for the introduction. I'm associated with Welltech University. Maybe I have not given my updates before. So today's session we can, I think we can start the session. So I hope you are all able to hear me. So I extend my thanks to the management of Nara Narasimha Reddy College. I thank the chairman,
Sir, voice is breaking, sir.
And I thank all the organizers for arranging this.
Now it is clear, sir.
And today's session is implementation perspectives of AI in medicine. And I am Dr. Raja, as I already introduced you. So in this AI-enabled AR/VR in communications and signal processing applications platform, I'm going to give a lecture on perspectives of AI in medicine. So first, as usual, many lectures I have given as implementation perspectives of AI in medicine. So the same thing I thought of giving, but later I made a little modification, and today we will concentrate mainly on generative AI, that is GANs, shortly called as GANs, so that are used to generate synthetic data, and that is somewhat cutting edge in artificial intelligence. So rather than going for general classification and the segmentation applications, I thought of going one step ahead. And today we'll go with the generative AI. And I learned from Sir, your HOD Sir, that Ravi Chand Sir, that the previous lectures are also about the basics of artificial intelligence. So, and also the faculty are attending. So I thought that more introduction into artificial neural networks, which they used to give in other sessions, I don't think that much is necessary. So I'm simply skipping all these things, the basics of artificial networks, and directly coming to the deep learning. So initially we will have some basics of deep learning. So starting from basics of deep learning, so we'll skip all these because these are all the basics. Then you go for the popular CNN models and we'll see what are the gold standard data sets, benchmark data sets available for research that are freely available. And we will see some implementation perspectives. So particularly today's session will be useful for those who want to do some implementation in Python. So for some implementation perspectives, we will see what are the Python libraries, why we need to go for Google Colab, and some implementation examples, as I told, CNN for MNIST. MNIST is handwritten character recognition. and optical disc segmentation that usually give, but today I have not included. I will give you the link, video link for whatever the code that I explained in other lectures. So that's also in chat. So today we will see the implementation of CNN for MNIST character recognition. So MNIST is a data set where handwritten characters will be there, and the artificial intelligence model will be trained to learn and test the data. So that is the simplest thing you would say. So any learning in implementation of deep learning algorithms starts from MNIST. And later we'll go for, as I told, generative AI and synthetic image generation using GANs, generative adversarial networks. So mainly these two code and implementation you see today. This is some preliminary introduction. So what is by deep learning? So what and all we need to know when we go for a convolutional neural network. So layers of CNN. So previously they are called as artificial neural networks or AI. Now it is deep learning. It is called as convolutional neural network. So I hope all are able to hear. Are you able to hear clearly?
Yes, sir.
Okay, fine. Yeah. To proceed, if there is any interruption, you please tell me.
Okay, sir.
So starting aptly with the different layers of CNN. So some people who have just now diving into the deep learning algorithm, so they want to know some basics about convolutional neural network. So what are the different layers in the convolutional neural network? So convolution layer, it has an activation function, max pool layer, dropout layer, and fully connected layer of that in the convolutional neural network. And this is what a typical convolutional neural network will be. So it has several layers of convolution, followed by max pooling and fully connected. So fully connected layers are the layers where the actual decision is done, where the actual
Sir, screen is not visible, sir. PPT screen.
yeah. Yeah, these are the several layers of a convolution neural network. Tens of a convolution layer, max pool layer, fully connected layer. The fully connected layer has a softmax activation function. The reason for using softmax activation function is internal. So what happens in all these layers? So the feature extraction and classification are going to happen sequentially in a convolution neural network. So what happens in a convolution layer? Let's see. So you want to understand about what happens in a convolution layer. You want to learn somewhat deeply in the sense you can study about you can study the textbook digital image processing by Gonzalez, and you can study the topic called basics of filtering in spatial domain. So that will be useful to understand how convolution happens in an image. And of course, the equation is given. Some people may be interested in the equation. So this is image xij is the image, and this is the filter coefficient. The filter coefficients are multiplied with the image, and we have dl is equal to 0. So this is the innermost loop which will be executed first. And these are different filters. So in a particular layer of a convolution, there will be several convolution filters available. So several convolution filters that is given by DL here. Several convolution filters will be operated on the image, and this is the value of the filters. And this is the row operation and the column operation. So that is how convolution operation happens. A typical convolution uh, filter is shown here. So what happens when we multiply this with an image? So for example, this is the actual image, 332, some values are there. So this is what happens in actual image processing. So image processing can be mostly thought of as matrix operations. So these matrix operations are nothing but when you place the convolution filter over the image and take the sum of products, there will be certain features that will be visible. So like if you use a high pass filter. So the filter I am showing here is a high pass filter. That is the two. It is horizontal filter. When you use this filter, the horizontal edges are evident. Likewise, when you use a low pass filter, there will be average information. So likewise, this is the very basic of convolution operation. Those who study signals and systems and values. And in fact, this FDP is organized by EC department. So better to computer science people. So we will be better knowing all this. What is by convolution? So this is what through the operation of convolution, the feature extraction happens in the image, and that is what happens in the convolution layer. So here we have the convolution layer where the feature extraction will be happening. Feature extraction will be happening. And not only one convolution layer, so the deep learning algorithm goes deeper and deeper, so there will be more and more convolution layers. And that is what we are extracting more and more features. And a simple retinal fundus image is shown, and the effects of convolution is shown. So the features are being extracted from the image. And this is how the deep learning model learns the image and extracts the features from the image, extracts the essence from the image. So after convolution layer, we have the activation function. So what is importantly an activation function also? So activation function gives the essence of the data. Okay, it is used to add some non-linearity to data after classification. So activation function is like instead of eating the fruit, we take the juice. So likewise, getting the essence of the data is done by the activation function. So some simple activation functions are shown here. So this is called as a saturated activation. Mostly during the machine learning era, the saturated activation functions are used. Saturated in the sense, after some time, the values become constant. That is called as a saturated activation. Coming later to deep learning era, we are going for unsaturated activation function like ReLU. So this is an unsaturated activation function. The reason is nothing but a vanishing gradient problem. So this I will tell about that little better. And as of now, as I'm telling, we have much scope to work on the activation function of the convolution because EC related people and signal processing related people can do some work in activation functions. But of course, it is a little difficult to prove the effect of activation functions on the CM. But still papers are coming, particularly if you look at journals like neurocomputing. So mostly they design a new activation function and propose for CM. So that aspect we can do. So coming back to the main discussion, that is, we have saturated activation functions before. That is, their value become constant. Whereas nowadays we are going for unsaturated activation because the value keeps on changing. It will not become constant. That is because of the vanishing gradient problem. What is a vanishing gradient problem? In machine learning, mostly saturated activation functions like sigmoidal or time H values. Whereas when we come for deep learning, unsaturated activation functions like ReLU, we have to use unsaturated activation function. The reason for to address something called as vanishing gradient problem. What is a gradient? Gradient is nothing but the rate of change of error with respect to gradient is the rate of change of error with respect to weight that is mathematically taken as rho e divided by rho w. So what is vanishing gradient in the sense? This gradient will become zero until the gradient is alive only. When the error change, when there is a change in weight, there should be a change in error. So until the gradient is alive only, there is learning. So weights are updated in neural network in proportion to rho e divided by rho w. But what happens, unfortunately, when we go for deeper layers, as you can observe, what is vanishing gradient problem? I'm just trying to tell. The back propagation of error happens. Let us see what is this L, what is this X, Y, and Z. X, Y, and Z are nothing but the weights. The weight in the next layer is Z. The weight in the previous layer is being X and Y. So what is going to happen? If this gradient is becoming very, very small, like for example, 0.001, this that is a gradient here, and that is multiplied with another small value. So then what is going to happen? This dou L divided by dou X is going to be comparatively much lesser than this dou L divided by dou Z. So in such a fashion, the weights, that is the gradients, get decayed layer before layer. So when the error is back propagated, the gradients are getting very much lesser. So that ultimately at one point of time, the learning stops. So that is what is the drawback there, called the vanishing gradient problem. If you use a very deep neural network. So this AlexNet, whatever I have shown here, is not a much deep neural network. It is a short neural network. Whereas if you go for a very deep neural network, what happens now? The vanishing gradient problem will happen. So for that reason, we are going for unsaturated activation function. Unsaturated activation function will keep the values alive. Okay, dou E divided by dou W will be alive. Gradient will be alive. and then the learning will be. That is what is the idea behind using VB. And these are all arrived to conclusion by using trial and error methods. And after the convolution layer and activation function, we have something called as max pooling. I am not diving into the mathematics of max pooling and all. Max pooling is as simple to remember that several sizes of types are taken and the maximum values are being retained. That is what is called as a max pooling. So this is done to reduce the overfitting. Overfitting in the sense, as we already saw in the previous slide, there are pools of data. There is so much of convolution layers and so much of learning is happening and so much of matrices are coming forward. So what to do now? We need to reduce the data. For the purpose of reducing the data only, we max pool. So the the maximum value of each tile is being retained. Okay, that is what is the significance of your max pool. And after that, we have fully connected layer. The fully connected layer is nothing but the entire artificial neural network where the learning will happen. They are included in the previous slide, but not taken to discussion today. The fully connected layer, that the actual learnings will happen. The errors are being back propagated, and at each layer, the errors and weights are being modified. And finally, in the forward pass, again the testing or decision is being done. And that is what is a fully connected layer. So coming back to some examples of popular CNN models. So AlexNet, as I have already shown here, this is the actual AlexNet. What are all there in the AlexNet? The AlexNet won the ImageNet competition. So ImageNet competition, actually ImageNet is not a data set. People think it's a data set, it's a competition. So AlexNet won the ImageNet competition of large scale visual recognition conducted in 2012. So it consists of 5 convolution layers. There are 5 convolution layers here and a max pooling layers of size 3 by 3. So here we have shown max pooling layer of from 4 by 4, whereas AlexNet uses max pooling layers of size 3 by 3 with a striding of 1. So ReLU is used as the activation function. In fact, AlexNet is the first convolution neural network to propose ReLU as the activation function. Seeing the success of ReLU in terms of fast convergence and diagnostic accuracy. So ReLU is continuously being used. So ReLU is used as the activation function. It accelerated the speed of training process by almost 6 times. That is the advantage of the unsaturated activation. There are 2 fully connected layers. The 2 fully connected layers are used for the actual learning. So you can see the full convolution neural network. This is for feature extraction and this is for classification. So the actual classification or actual learning happens in the fully connected. And then finally, you have a softmax activation. I will tell about the softmax activation function at last. The softmax activation function is a probability map. That is, it gives the values in the range of 0 to 1. And that is useful for us to make the decision. So we can do the thresholding by like saying 0 to 0.4, it belongs to class 0, and 0.5 to 1, it belongs to class 1. Likewise, we can categorize the data. That is the ultimate use of the softmax activation. But after that, coming to the next one, since AlexNet, the state-of-art CNN architectures is going deeper and deeper. So after that, the trend has been becoming like adding more and more layers for a convolutional neural network and becoming more. So while AlexNet has only 5 convolution layers, the BGGNet and GoogleNet has 19 and 22 layers respectively. So the trend of deep learning has become including more and more convolution layers rather than doing some novelty in changing the architecture or changing the activation function. So nowadays the interest is to add more and more layers and get more insights. So that's what's the problem in increasing the network depth or the number of layers. That's what, as I told you already, vanishing gradient problem occurs when you increase the layer of a convolutional, when you increase the number of layers in a convolutional neural network, the vanishing gradient problem occurs. Deep networks are hard to train because of vanishing gradient. As a result, as a network goes deeper, as the network goes bigger, its performance gets saturated. Saturated in the sense there is no learning at all. That's what. So ResNet has become as an alternative with the skip connections. So these skip connections will solve the vanishing gradient problem by what means now? The error flows through the bypass channels. The residue, they call it as the residual connections. So that keeping alive the vanishes, keeping alive the gradients. Gradients are kept alive through the keep connections. So ResNet has become successful like that. So as you can see, so many convolution layers are there. Because of these keep connections, the vanishing gradient problem is being avoided in a ResNet. That is how ResNet became very popular and so much implementation on that. Even though people are implementing UNet, in UNet layer some architectural changes they want to do now. In UNet itself, they used to implement the skip connection. So these skip connections are certain. The vanishing gradient problem is avoided. The actual gradients pass through this skip connections so that the problem which I told already, the value is getting lesser and lesser. So you assume that this value is flowing directly to two layers before. Then what happens? This gradient is kept alive. That is what is the advantage of a SLAM. Figure shows a 34 layer ResNet. So it is deep, I told you. How many layers are there? 34 layers are there, which has deep connections. There are many editions of ResNet, ResNet 13, 14, 15, like that, so many ResNets are there. Proposed with the number indicating the number of layers. ResNet 32 in the sense, sorry, ResNet 34 in the sense, there are 34 layers we can understand. Likewise, so many ResNets have come, so many editions have come. The skip connections offer an alternative path for the gradients to flow during the back propagation and avoid the vanishing gradient. So that is what is the advantage of your ResNet. Looking at today's content, in our content, I told you popular CNN models. Some models I have told you. So AlexNet, GoogleNet, I told you, and the ResNet, what is the ResNet, I told you. And commonly, what are all there in all these CNN are nothing but convolution layer, max pool layer, dropout layer, activation function is there, and apart from that, fully connected layer. So what happens in the convolution layer? The feature extraction. So as deep learning evolved, there are more and more convolution layers used. So there is an abundance of data. For that reason, we use max pooling. And after that, we have dropout layer also, which I have not covered today. And then we have fully connected layer. Fully connected layer is a layer where the actual learning of weights happen, mimicking a human brain. So this is what the error being committed goes backwards and the fresh weights are being taken. And that is what is the learning process. The actual learning process and the change of weights happen in a convolution neural network in the fully connected, in the last fully connected. And purposely we use a softmax activation function at last. So the reason that let us see whether the softmax activation function is also given. Yeah, softmax activation function is given. The values range from 0 to 1. The purpose of using the softmax activation function in the last layer is particularly in classification because it is a probability now. The value will change from 0 to 1 so that we can threshold either near to 0 or 1. If it is taken as 0, that is abnormal. If it is taken as 1, it is taken as, if the value is taken as 1, then we can assign it to a normal class, something like that. So it is a classification problem. If it is a classification problem. Next, we go to data set, the first point to accomplish. Okay. So what is the data set? So whenever nowadays we are doing signal processing or image processing projects, not without the machine learning or deep learning. So the ultimate thing we should be concerned about is a data set. So some data sets I will introduce. So if you are not already aware of these things, you can just so the name of the data set is MNIST. So as I already told, MNIST can be thought of as the hello world of the machine learning problem. That means it is the first code. Any new CNN model one person has developed, the first thing to be tested with is MNIST. It is the preliminary used to experiment with different machine learning algorithms and then to compare their relative states. MNIST is often the first data set researchers train. And ML researchers say if it does not work on MNIST, it won't work at all. So this is the basic thing which is going to be used as a data set for machine learning algorithms. What is it actually? as we can see in this, the handwritten characters starting from 0 to 9. The simplicity of this data set is we need not download this data set and keep in our machine. It can be called online into our code, and it can be executed online into our code. That is the simplicity of MNIST. And in fact, this is the first thing to learn, but this is not the only thing to learn. So suppose you are going for a deep learning based FDP or something. No, I don't mean this FDP. You invest lots of amount and go for some training in the sense. You see the last experiment or last task of MNIST, that is not useful at all. So whatever algorithms that mostly work with MNIST, they used to fail with others. Okay, because MNIST is a very basic thing. So I have seen courses like in Udemy and all, beyond MNIST, testing the algorithm beyond MNIST. So when they keep the name itself as beyond MNIST, that means MNIST is taken for granted. So whatever testing you do, that is going to work with MNIST. So that is not like underestimating the data set, but that is not the only thing to learn. That's what I wanted to say. What it consists of now, it consists of the handwritten digits by different people. And there are totally 70,000 black and white images of size 28 by 28. So whatever image we see are of size 28 by 28, and there are 9 classes. So in fact, it is written wrongly. There are 10 classes starting from 0 to 9. So here 60,000 images will be used for training and 10,000 images will be used for. So today you will see one Python code classifying this MNIST data set, and directly you go for GANs, generative adversarial. And next to MNIST, we have fashion MNIST. What is fashion MNIST, as we can see? It has the images of different clothings and different male and female wearings, like shoes, like shirts. Okay. It is a data set of Zalanda's article images consisting of, this also consists of 70,000 examples. So after MNIST has worked with, what is the next level now? You can go for fashion MNIST. This also has 28 by 28 sized images of n classes. Fashion MNIST serves as a replacement to the original MNIST dataset for benchmarking machine learning algorithms. So next level, after doing your testing with the MNIST, you can go for fashion MNIST. And coming to my domain, that is here Kaggle repository. Kaggle is not a place for single dataset. It is a repository. You may be knowing. So nowadays, even UG students are aware about Kaggle datasets, where we have several datasets. One of that is diabetic retinopathy. Because I work on these things, I am just showing this. The diabetic retinopathy dataset consists of 5 classes of images. Totally 35,126 color fundus images are there. Anybody can download it. Go to this website and download this diabetic retinopathy dataset and develop an algorithm to classify all the 5 classes, get accuracy, better accuracy, and define a new series model, and that can be 5 classes of diabetic retinopathy, and their labels are in separate. These things are we need to take while doing the code. So some of the data sets, how we maintain the data, class in separate folder, class 2 in separate folder. Whereas some of the data sets, what they do, they essentially name the images and they keep it in a folder, and they have another Excel where in sequence the labels will be. So you have to code accordingly. So take the first image and they take the first value of the Excel. Take this image, loop, like that. The reason can be free for you. Next interesting data set is the so these are related to my domain, all are retinal images. So the data set is contained by Hyderabad, where you have to register and get the images. Here also the data set is free, but you have to register your email ID, institutional email ID you have to register. Then you will have the ability to download the Here 50 images are taken for training and 51 images are taken for testing. What is available in this data set? The fundus images and the segmentation maps. This is what we call as a segmentation map. So this is a classification data set and this is a segmentation data. This is a data set meant for segmentation. The data set meant for classification. This is the data meant for segmentation. So what we do as the supervised learning using this data set? This particular pixel corresponds to optics. This particular pixel corresponds to optics. This particular pixel corresponds to optics. So likewise, unlike here, each image is 90, each pixel is 90. So the data set is very small. Okay, 50 plus 51 images are only there. Not one images are only there. Compared to that way, 126 images, it is very small. The thing is, here each image is an entity, here each pixel is a class. This will be taken as a this pixel will be taken as optical display, and that's what. So when you want to do some experimentation with the segmentation, CNN based segmentation, you go for and download the. It's a very popular department. In the last 4 to 5 years, professionals have come with using this TGS. In fact, this is the benchmarking data. And then just have a look at the cats and dogs data and have a thought that how it is different about it. Compared to these data sets, they are very standardized. Standardized in the sense the sizes of the images are very standardized. And where the actual data is occupied within the entire data, that is being very much standardized. We have data sets like this also, cats and dogs data set. It is not a line of research which is very much similar to medical image also. As I already told you, medical images are very much standardized. Whereas this is also another type of research where you may keep on developing algorithms to properly diagnose, properly classify cats and dogs. So irrespective of the position of the cats and the dogs, so not only imaging data sets, we have the data of death probability for COVID-19 patients. So you have another data set like this. I will give the link for this data set. So what are available here? It consists of 1,600 patients, COVID patients records, and there are 13 features about these patients. It is available, freely available on national database of drug. So if you want to download the data set, you just copy for the you know, search in Google also it will be available. National database of, and using this data set only there was a publication prediction of death status of the course of treatment in SARS-CoV 2020. The paper was published. So it's a very good journal. You go for this journal. All this type of medical image or medical database classification, they are given with score also. When I with this journal and I download the papers and also. What is available in the data? Age, sex, diabetes, hypertension, cancer, renal problems. So in combination with COVID severity, so the doctors will not be able to say only based on the COVID severity, the patient will be surviving parameters they have to see. So based on real-time testing, all these data are being evaluated. So based on this, you can have a new set of data and what will be the outcome that we can classify based on that. And where to find suitable data? That's an interesting thing. So the website says the best public data for machine learning and data science. So what I just put this in meet. So what you have Kaggle, UCI machine learning repository, so not digged into much this. Mostly work with Kaggle, work with that diabetic retinopathy and glaucoma. For glaucoma, we have data sets like one. So with that, I restrict my. So, if you're interested, you can to us. So much is that. Use that for most of the image processing applications. Coming back, so types of data sets. What are the data? So if you are new to using Python, so we are still over matter and we want to get Python. In that aspect, these discussions will be useful for you. So what are the different Python libraries? NumPy library is useful for array, vector, and matrix operations. You want to do any matrix operations, like in MATLAB we do multiplication of matrices, transpose of a matrix. Like any matrix operation, as I told, data processing at one point of time, it is not always matrix operations. So image processing operations are always done by library. This is suited for numerical data. Numerical or quantitative data. It is not useful for qualitative data. So this is what we call it as a quantitative data. The case everything has a mean. So the mean the matrices only with numbers. Those are certain quantitative inputs. So for those quantitative inputs, we go for tablets to build these tabular data sets. These tabular data sets cannot be used in NumPy. Only typical matrices it will take. To operate on these tabular data sets, we go for pandas. Pandas provide performance easy to use data sets, manipulating numerator and base data. Data manipulation, import, analyze, everything you can do. It is best suited for tablet. And we know Keras and TensorFlow. These are machine learning libraries used for data pre-processing to build and evaluate a model. This Keras and TensorFlow almost is any operation that can be done with Keras can be done with TensorFlow also. They are given by different companies. That's it. And we can learn TensorFlow also. And TensorFlow was developed by Google Brain. We can develop more complex networks. So they claim that compared to Keras, more complex networks can be developed with the TensorFlow. As we have seen in model, whatever it is, AlexNet or ResNet, these type of CNN models can be built, compiled, and tested using the libraries like Keras and TensorFlow. And OpenCV and PI. OpenCV and PI are computer vision. So the PP computer OpenCV stands for computer vision. These are image libraries just to fetch the images, resize the images, arrange the images, and then do basic image processing operations like pre-processing, all the pre-processing. So any image processing operation can be done using the OpenCV or PI. So OpenCV and PI they are used for image processing operations. Keras and TensorFlow are used for machine learning operations. Just like we have these toolboxes in MATLAB. MATLAB we have several toolboxes, whereas here we have libraries. So we have to download and put all these libraries into your Python framework. So of course nowadays all are started using Python. I'm just giving this intro for everyone to be covered before we go into the actual implementation. So how to install? So first you have to install Python and Anaconda. So once you install Anaconda, there is a front end for execution. Then you can install OpenCV based on your application. So of course, you're going to involve in image processing project. Now you have to install OpenCV in Keras and tasks that can be accomplished with the TensorFlow that can be 10 times easily done with Python. I'm trying to learn Python, which is much. What otherwise you can install Python instead of installing all these things. After installing Python, you have a user in Google. Once you have the user in Google, if you have a Gmail, the Google Colab can be taken. Codes can be executed on Google's cloud service. So you need not execute your code in a laptop computation itself. So whatever the things we did in MATLAB previously. So when I did my PhD, when I wanted to improve the ANN's performance, so I want to go to 200 images from 150 images. The computer becomes very, very slow. So that was the case 5 years back, 5 to 6 years back. Now we are casually dealing with 35,000, 45,000 images. That is because of the Google's cloud servers, and we connect our Google Colab, the notebooks to cloud. So that's why we need to install Google Colab also, not install. We need to have a user ID in Google Colab. So automatically the installation of this Keras TensorFlow and OpenCV will be taken care. And that is the best thing also. So sometimes if you have your local Python only, they install Anaconda and then Keras and TensorFlow you separately install in the sense there is always so much of compatibility issues between Keras and TensorFlow. So because mostly we won't do the coding from the scratch, we take the code from somewhere and we have some piece of code already available. We will always keep on mixing those things and see some try to make our ultimate goal. Okay. So in such cases, we'll use Keras also, we'll use TensorFlow also. At that time, what happens? There is always compatibility issues with whatever installation you have done with Keras and Tensor. But if you go to Colab, all these issues are automatically. Yes, you can leverage the power of Google hardware, including GPUs and GPUs, regardless of the power of your machine. So that is what is claimed in the Google Colab website itself. Regardless of the power of your machine, you can use GPUs and the CPUs. As far as concerned academic research, whatever cloud space that is given by Google freely can be itself is sufficient. Sometimes if you rigorously work for some 20 days, that time the monthly allocation is over, like that you will get a message. That is very rare also. So otherwise you can keep on working with Google Colab free. There is no need to go for subscription. In fact, subscription also is around some 1,000 rupees per month. Not a bigger month. It is a Jupyter notebook environment installed with Keras, TensorFlow, PyTorch, OpenCV, etc. Google Colab is a Jupyter notebook environment. What is given for last. With all these introduction, because directly jump into the coding part. So I'm just recollecting what is already doing. And have a look. Shortly we'll go to the coding part also. Thank you for the data. This is the data set from here. The whole data set I took. Into that there are several data sets. Saw as example. One such thing is the data set. And this web link also I have given. What are the Python libraries itself? And what are all the essentials to install? Coming to the actual coding problem, even for classification using this sample code is done in the Google code in my own Google call on how the MNIST data is classified. And make a small code to generate. Before going to the generative adversarial networks, first see what is how it is done. So first connect to this Google Colab. So here you see the RAM and disk. Means RAM and disk being allocated by Google sources. So we need to import the necessary libraries. Here in fact, we need to import the data also. So I forgot to tell one thing. MSc data set is being offered by the Keras library itself. Okay. Model does to test it immediately. Keras itself is giving a data set called MSc. Then import sequential. So all the models we are using mostly are sequential models. What are sequential models and models? Sequential AP, sequential application programming interface, and functional API we call it. So sequential model is equal to the first layers output will be the second layers in. There is a sequential progress of data. That's what is sequential modeling. Some RESTnet implementations are taking functional API. So for functional API, we can implement that. So because parallel connections are there, branching are there, you have to go for functional API. That is what. So all these models we have to import here. And then here also it is import to categorical. What is the categorical? We need to deal with categorical data. Categorical data is nothing but the qualitative data. That is label 1 or label 2. So whatever is data I have already shown here. So each belongs to a class. So this is class 0, this is class 1. That is label. So we need to deal with categorical data. So we need to import corresponding library called import to categorical. And after that, next dot load underscore data. The output should be extrain, y-train, express. This is the simplicity with your MNIST data set. So you can directly call the data set and segregate it into training data and testing data. As I already shown here, out of 70,000 images, 60,000 images will be used for training and 10,000 images will be used for testing. And you are not seeing the last column. The last column uses the actual class belongingness of this row. Okay. That will be 0. That will be a proper 0 that is defined type in the computer. Proper 1 type in the computer. That will be the class 0. That is categorized into extrain. So extrain is the actual data. The y-train is the label of the training data. Extrain is the actual testing data. And y-test is the label of the testing. So you are downloading the data set. So if you run this particular line, the data set will download. And after that, we are imported NumPy library. So when you view NumPy shape of extrain, it gives the shape of extrain. So NumPy is mostly used for matrix operations. When I want to know the shape of a data, it should be a NumPy. When you can know the shape of data, NumPy is the shape of extrain. So what you can see is 60,000 images are there, 28. There are 10,000 images 20 by 28 by 20. Similarly, y-train and y-test. So you'll be knowing what is your extrain, y-train, x-test, and y-test. So look at a feature matrix is like this. So one image is there. Several features we are extracting from the image. These are said to be extrained. The label of that particular image is said to be, and this is the training data. So you go for the testing data. So whatever features you extract from the testing image, those are said to be expressed. And the class that corresponds to is y-test. So explain y-train, express y-test. And the y prediction is predicted by the algorithm. So error is calculated as y predicted. So here we are going to segregate the data into extrain y-train, extest y-test by a simple command itself. And then we are loading the image and seeing the image. So for example, 5,999 image, just to show you in the sense that is showing handwritten 9. Then we are reshaping the data. Extrain dot shape of 0 in the sense. So what is the shape of extrain if you see? It is giving us 60,000, 20, 28. So extrain of 0 in the sense, this will be taken. Extrain of 0, extrain of 1, and extrain of 2. So here extrain of 0 in the sense 60,000. So all the 60,000 images are reshaped to a size of uniform size of 28 by 20. That's what is meant here. In the next line, what we do now, we normalize the image. Okay, so that the image values. So as you know, the grayscale images are in the range of 0 to 255. So we divide by the maximum value of 255. Now all the images will be spanning from 0 to. Then for y-test and y-train, as we have already seen here. weight train and weight test. So weight train and weight test can only be labels. For example, the value of 0, the class of 0 does not tell its value as 0. Similarly, the class of 1 does not tell its value as 1. They are qualitative. We emphasize that we have this particular line here. That is nothing but heras.utils categorical. So it converts these values to categorical. And then we are defining the model. When we define the model, we are importing the model as a sequential model. As I already told, it is a sequential model. We are adding convolution layers. This is a very much tailored CNN, very small CNN. It is not a conventional ResNet or AlexNet. It is taken from our own example itself. Different layers are taken from our own interest itself. So convolution, drop out to flatten, dense layers. Dense layers are nothing but the last fully connected layers. As I have already shown the different layers of a CNN, convolution layer, max tool. So those are implemented here. Fully connected layers implemented by time. Dense of 120 means 120 units are there. Okay. So these are taken random unless the last layer should be taken for the analysis. So look at a simple neural network architecture. We can see here. We want to classify into 3 classes. There should be 3 units at the last. Okay. That's what gives a probability of the first class, second class, and third class. These are probability maps. That's why we are having top max as the activation function of the last unit. So this value is 0.7 and this value is 0.2 means this value is equal to 0.1. If you add everything, the value will be equal to, value should be equal to 1. Okay. That is what is the last layer. And importantly, whatever may be the number of classes you use in the problem, that many number of layers should be declared in the last layer. That's why we are promptly given as num classes. And then you are compiling the model. So when you are compiling the model, you have categorical cross entropy. What is it I will tell you? So there is a loss function that is going to estimate the difference between the actual value and the expected value. That is like error. And you tell the optimizer and what is the metrics we use to take. And what is the categorical cross entropy? When you go to generative adversarial networks also, the categorical cross entropy will be very much useful. So this is the last function called categorical cross entropy. So minus 1 by yi logarithm of p yi. That means yi is the y test and the probability of yi is the output of the AND. That is nothing but the y predict. yi probability of yi plus 1 minus yi into log of 1 minus probability of. So this is the categorical cross entropy. And that is what we declare here in the function. And then we fit the model, telling X train and the Y train, and validate with the X test towards Y test. The learning is done with the X train towards Y train, and we need to test with the X test towards Y test. So finally, we are evaluating the model. We are evaluating the accuracy, how it is classified, validation accuracy and test accuracy. So I told this MNIST is a very simplest classification task. It is the starting point of any deep learning network. So with this introduction, so anyone who has not touched Python, we have learned several things. That is nothing but we have an environment called Google Colab where we can connect to cloud and operate on the data sets on online itself. And initially we need to import all the data sets. Because Python being a free web, not like MATLAB, we are not purchasing. We need to import all the credits initially. And then data sets like MNIST can be directly downloaded from the cloud. And several operations we did, some pre-processing operations like converting Y train and Y test to categorical values. So all those things we did. And then we defined a model, a sequential model with convolution layer, dropout layer, and the dense layer. So here we are not using max tool layer. So what is concluding of 30? That means 30 filters are used. As I have shown here, when I explained the convolution layer, I told that several filters will be used. Here only filters are used. Multiple filters will be used. So it's a single filter example shown here. Multiple filters will be used here. That's what. Usually they'll go for 30 filters or 40 filters. It's a simple trend here. Okay, you can keep on changing the values. 30 to 50 is not going to affect the decision in any way. Sometimes it may increase, sometimes it may become overfit also. What is the overfitting? We can do this. The activation function we are using is reduce. That's what I told in deep learning. We are always going for the unsaturated activation function by. And you should be knowing what is by a loss function. What is the metrics, actual metrics. So how I have improved, whether the algorithm, whatever I have designed, working on improvement or not. That is decided by the metrics. We have a matrix called accuracy. And the optimizer we have added. Coming to the important part of is whatever I have taught so far is to understand the further things. Generative adversarial networks are very, very interesting. So I told the CNN for classification using MS dataset is completed. Some segmentation work, if you are interested, you can go to my YouTube channel. I have already several this software is an optical factor. But you can go through. And if you want any further explanation or code or data set, you can always contact me. So you can write to Raja. The segmentation algorithm is working fine. Want to some segmentation and we can go further. The collaborative search or whatever. Due to segmentation, just go through. Because every time I go for algorithms and segmentation, so let us have impact on something that is new, like generative AI. Generative AI is very interesting. Why? Because all the other artificial intelligence model, whatever we have been doing, they are not giving anything in our hand. It only gives us to, it only makes us to take the decision. But generative AI goes further and gives us some data. Fake data, synthetic data is being generated. So human faces are being generated. So if you can go through the internet, these are all GAN generated human faces. These people don't exist in reality. Okay. By training a neural network, the human faces are interpreted by artificial intelligence models. So these are the faces that are artificially generated. So for a long time I have been talking, but I think it's clear and all are listening. Hello. No response. So coming to the generative AI again, so that is at our hands to generate synthetic data. So data is always in scarce. Suppose a new disease has come, like COVID-19. So initially we don't have much of the images with our doctors. We need to train our deep learning algorithms to use it. Only few hundreds of images are available of chest X-ray affected by COVID-19. So what we can do with those 100 images, we can generate thousands of images using generative adversarial networks. So that is what is the interesting explanation and coding part we are going to see now. These are all the GAN generated human faces, and in medical applications, this shows a CT image of a human skull. This is original, and these are all generated by the GANs. Okay. So as much as we cannot observe any much difference between these and these. So the success of GANs will be properly generating the normal data and the abnormal data. And here comes another interesting example. This is collaborative imaging data. This forgot the name. Interdisciplinary image generation. That is, they train the GANs with the MRI and CT image. And further, if you give MRI image only, they will generate the GANs will generate the corresponding CT. That's what we need not go for CT imaging itself. Initially, the GANs are generated with MRI image and the CT image of the same person and the same anatomy. And the GAN gets trained with multiple images like that, then we can go for an MRI image alone. So the GANs are capable of generating the CT image. So it's not like a magic. So papers are published like that. So if you look at this paper, I forgot the name, but cross-modality medical image estimation. So cross-modality medical image estimation, you have two modalities, CT and MRI, where if you train the GANs, generative adversarial networks with the CT and MRI of the same person and same anatomy for several hundreds. Newly, if you give the CT alone, MRI image will be generated by the. So these are very, very interesting things that is going to be trendy in the future, not right now also. Right now it is happening little. So in the future, GANs will be there.
Their voice is not visible, not clear, sir.
Yeah. Just now the Bluetooth connection got disconnected.
Okay, sir.
Sir, Raja sir.
Yeah, sir.
So nice, sir. You had a great
please tell
session,
me,
but
sir.
I couldn't be in the session for complete duration.
Okay,
It was
sir.
with a different assignment.
Are you able to hear me now?
Yeah.
Now it is clear, sir.
Shall I proceed?
Yes, sir.
Because my Bluetooth is not connected, but still you are hearing. That's what I am just surprised. Okay, whatever. So as I told you, this is called as a cross-modality image generation by using GANs. So that's what is a GAN? Let us see. Generative adversarial networks is a deep learning architecture that consists of two neural networks in competition against each other. So there are two neural networks that is called as a generator and a discriminator. They work in competition with each other. That is in the sense. What happens in the sense? You have two things. Generator. Generator takes the input from a latent noise variable. So here you give some noise variable as input to the generator. So the generator will be generating some random noisy image. So it is not at all relevant to the original image which you want to generate. Some noise is being generated and that is given to the discriminator. So at one point, if you see, the discriminator will get the images from real samples and also from the generator. So what we start doing initially we train the discriminator properly. That is properly in the sense the original image when we are giving, we call it as a label 1. So we train the discriminator by saying the original image is original itself. But later what we do, the generator's image is also told as 1. So we are trying to fool the discriminator. So what the discriminator will do after a certain period of time, instead of learning the fake inputs, what it will do now, the discriminator will try to twist the truth. Twisting the truth in the sense, what it will do now, the generator and the discriminator will act in collaboration and start generating the images that are similar to the real images. That is what is the interesting part with the GANs. So I think it is little pretty confusing. Okay. So I also got confused even after implementing the code also. Now also I have to study once again to get to the concept again. So that is what is happening in the generative adversarial network. We have a generator and discriminator. The role of the generator as it implies, it is used to generate some fake data. Fake data is generated by triggered by some latent noise variables. So some noise variables are given as the input in the sense. It will generate fake images of same size. Okay. So initially the images will be totally different compared to the original image. Suppose I fundus images are my original targets in the sense. This real data sample will only have that real I images, whereas for the same size, some noise is being generated here, and that is given to the discriminator. Initially, the discriminator is trained properly, in the sense whatever real data that flows here, that is trained with the label 1. So as we have the supervised learning everywhere. What is the supervised learning as we know? The last thing is nothing but the label. For whatever features extracted, the last column is nothing but the label. So is here. In the GANs, the supervised learning is done by taking the real images as 1 and fake images as 0. So the discriminator starts learning all these, and after that the fake images generated are also labeled as 1. So then what happens? The discriminator's loss function becomes enormously large. So what always artificial neural networks tend to do? Artificial neural networks tend to reduce the loss function. So after the generator and discriminator training and evaluation, we have a combined model phase also. In the combined model phase, what is happening? Both the generator and discriminator will act in combination, so that what will do, the discriminator will twist the truth. Twisting the truth in the sense, for the label it will start generating the data. So at a point of time, after several iterations, the data that is being generated by the generator will start resembling the real data samples. That is what is a generative adversarial network, to put in a theoretical perspective. Generator generates fake samples of data, maybe it may be an image, audio, etc., tries to fool the discriminator. The discriminator, on the other hand, tries to distinguish between the real and the fake samples. The ultimate aim of the discriminator is to properly detect whether it is a real data or fake data. The generator and discriminator run in competition with each other in the training phase. That is, during the training phase, they act as opposition. Okay. At one point of time, they act as a combined model, and then make the fake data similar to the original data to reduce the loss of the discrimination. So that is what is happening. The steps are repeated several times, and in this, the generator and discriminator get better and better in the respective jobs after each. So that is what. So when you go for a GAN, generative adversarial network, the loss function is very important. So as I told you, this binary cross entropy loss, where YA is a Y true, there is a ground truth, and the probability of YA is a Y predicted. There is a prediction from the artificial neural network. Inspired by this binary cross entropy model, here also we have the loss function. So what is the loss function? What is the discriminator's output to X? What is X? X is the sample data, that is the original data. Discriminator's output to the original data, followed by discriminator's output to the fake data. So X is the original data and Z is the synthetic data. We have designed the loss function. We have designed in the sense it is already implemented in GAN. So generator's output. For the generator's output, what is the output of the discriminator? So two models are acting in series. The output of the generator for which we get the discriminator. And here the constants are nothing but the data that is taken from the real data and the synthetic. E is nothing but the samples from original data and the synthetic. So this is the loss function of the GAN. So we'll see the implementation of GAN also.
Maybe student theory or lab.
So this is these are the original images which are taken, so which we are generate synthetically by using GAN. After the implementation of GAN, whatever synthetic data that is generated is, but you have successfully generated GANs anyway. Maybe by changing the loss function or by increasing the number of iterations. At one point, we can become successful in generating synthetic images by using the GANs. So what is the coding perspective, as I already told you? So like we saw in the MNIST example, we need to import the corresponding libraries, okay, TensorFlow. And in fact, the layers also we are going to we are connecting to our Google Drive. So these are the lines in which we connect to our Google Drive. In my Google Drive, I have a folder called images. So to that it will. Okay. So here we have some lines of code to pre-process the images. This is ultimately image reprocessing operations, like reading the images and resizing the images. And then we have extrain. Extrain is nothing but the training data. Okay. As usual, as I told in the previous example, if I take as numpy or shape of extrain, it will show how many images are taken. 101 images are taken, each of size 28 by 20. For my own interest, I'm seeing the input. Suppose we are designing an amplifier experiment. Okay. Application of sine wave, we will see. Before that, what is the original input is properly coming or not. So likewise, we will observe the actual input also. What are the inputs that are being taken? And then again some pre-processing operations. So we are taking some variables n comma h comma w explained or shape in the sense. It will take the number of rows and number of columns and n is the number of images. N is the number of images h comma w. So when you go for the coding aspects of deep learning architecture, it is always important to have in memory the shapes and sizes. Okay, how many images we have taken? 101 images we have taken. Each of size 28 by 28. So those things are taken in these variables. The D is a single variable where we multiply 20 into 20. So sometimes when we are training the CNN, we are not taking it as a matrix. We are taking it as an array itself, and then we are training the CNN. So D is taken 28 by 28, which is nothing but 784. And now if you put the numpy or shape of extrain, it is 101 images, each of size 784. So that is what we call it as this images are being flattened. And regarding the implementation of GANs, I have given another slide. There is nothing but how this particular code is being taken to reality is, first we have to define a generator and run the generator. First we have to define and run the generator. Then we have to define and train the combined model. So that is what the sequence of operation happens here. So for comparison between the sizes and compatibility of sizes, they are given in this order. Whereas in actual implementation, we will define the generator and define the combined model. These two things we will do first, and then we will run the generator, and then we will train the combined model, and we will see the output of the combined model. So these are the steps worthy remembering to know how this particular code is being working. First, we have to define a generator and a discriminator. So generator plus discriminator is called as the combined model. First, we have to define. What is by defining? Defining is nothing but what are the different layers that are there in the particular CNN. So it is worthy remembering that both this generator and discriminator or generator plus discriminator combined model all are nothing but CNNs, convolutional neural networks. So we are going to take them. And what we are importantly interested to see about their sizes now, the input we are giving to the generator is of size 100. That is, a 100 length array is given as noise input. So based on that noise input, the generator will generate an output image of size none, 780. So in deep learning algorithms, we get this none in the sense that will be useful for later adaptation. Later adaptation in the sense that size can take anything in the corresponding operations. 784 now. When you use the same entity again, that can be taken to any value. That is the advantage of taking this 782. So otherwise, when you see in so many codings, always there is a none, comma, 1, comma, 2, something like that. So that is useful for that. So coming back to the discussion, you have a generator, you have a discriminator. So what you do in the generator, by giving an input noise of size 100, you generate a fake image of size 784. The 784 is nothing but a flattened image of size, actual size 28 by 28. Then you run the generator. When you run the generator, the actual input noise we are giving is 32. What is the 32? 32 is nothing but, so only when you understand these numerical values, you can understand the code. So all these, what is the 3200? Why he is saying this? All these are meaningless. Instead of 100, if you give 200, what is going to happen? So if you are tired of learning this code, understanding of the code is difficult. So that's why I'm telling you. So when you run the generator, you give a input noise of size 32, 100. 32, 100. So if you want to understand the code, you may take a note also. Otherwise, it is going to be a difficult task to understand the code. So 32 is a batch size. So batch size in the sense, if you have some 100 images also, they are trained and validated in batches. So in a batch, we are going to give 32 images and we are going to generate 32 images. That is what is of 32. And the 32 noise sequences we are going to give as an input. So you please understand one thing. This generator is going to generate fake images by taking noise sequences or noise vectors. That is what we are doing here. So 32 batches of 100 values, all these are noises. So when you run this, what will be the output of the generator in the sense? They give 32 images of size 784. They are nothing but the fake images. They are not original images. And then after running the generator, we have to define a combined model. So combined model combined with the generator and the discriminator. You need to have a deep thought why this is one instead of 7. Why this is one in the sense, what is the discriminator ultimately going to say? The discriminator is not ultimately going to produce any image. The discriminator is going to give only a decision whether it is a synthetic image or original image. So our logic is, if it is a original image, the output will be equal to 1. If it is a synthetic image, the output is going to be 0. That is why when we have this sizes, understanding these sizes are very, very important when you want to implement a deep learning model. 100, 1. Okay. And after that, training the combined model by giving 32 batches of noise sequences of length 100, you are going to generate 32 decisions. So this is less important. So in between what is there now, the combined models output, you will take it as the GAN generator. That's what we have done in the coding part. GAN generated images freely available internet. Freely it is available. Freely it is available only with online data sets. But later we developed the code to take the images from specified folders and generate the images of our own interest. So that is what is the minor task I have done to implement this GAN. So whatever inputs I am giving, so based on that, the GANs are able to generate. So let us dive in coding. So little bit I have told. We are at the level of building the generator and the discriminator. As I already told you, this generator is nothing but a CNN. So data dimension 100 in the sense, you are giving a noise sequence of size 100 as input to the. However, maybe in between happening is not our interest. Finally, what is the size of the input and size of the output? That is where we will be safe without getting any errors. We go for a deep learning model. Here you can give 256 instead of 256. You can do 2056 also. Not going to affect coding. Whereas the input and output sizes should be taken. But anyhow, what are all there in between? There are dense layers. As I already told you, the dense layers are nothing but the fully connected layers where the actual learning will be happening. So here convolution layers are not given in the sense, it means that there is no feature extraction here. The data is learned rawly. That is what is the meaning that after input you have dense layer now. The raw data is being learned by the CM. That is what here. And after that building the generator, you go for building the discriminator. For discriminator, what is the input size and output size? It is none, 100. So here we can infer the different layers of your CNN. And finally, the discriminator summary is, it takes the fake images generated by your generator and it is given as input to the discriminator. Matching. This is it. Okay. The generators, fake generated images are given to the discriminator. That is what is accomplished here at this point of time. Still, we are not running the model. We are only defining the model. Defining the model in the sense we are going to say what should be the different layers that should be available in the discriminator, generator, and the discriminator. So after defining the model, we build the model, build the discriminator, and then compile the model. Okay. So discriminator is the model that is built for a discriminator CNN, and this is it. Okay. So when you look at the shapes, what we can see now, those fake images that are being generated by this generator has given us input to the discriminator. And already I told importantly, that is, when you look at the output sizes, it is very important to understand. The output of the combined layer will be always equal to 1. Why? Because it is always a decision. Okay. Discriminator is not going to produce any image. Generator is only going to produce the image. The original data set is also going to give the image. The discriminator is going to tell whether it is a 1, that is, if it is taken from the original data set, or if it is a 0, if it is taken from the fake data set, that is a generator output. Okay. So the output should be either 0 or 1. That is why sizes are standing as 1. And after that, what we have to do now? Create an input to represent the noise sample from latent space. So latent dimension in the sense we are given 100. So we need to generate a vector of size 100 with which the noisy images will be generated. So generator of Z we are giving, and the fake prediction is equal to discriminator of the image. So discriminators output to the generator. In fact, this is the line where we have this particular entity. You all know, like D of X is the original input given to the discriminator. Z is the fake data given to the generator. And the fake data, fake image generated by the generator is given to the discriminator. In fact, that is the line here. It is going to give the generator of Z, the output is given to the discriminator. This is what you have as a fake prediction. After defining the generator and discriminator, we have to define the combined model also. What is the combined model? This model is little different from whatever models we have seen so far. This is different. This is also a model. Discriminator is also a model. Build discriminator is also a model. So these are all defined by us. These models are defined by us. Whereas with capital M, if you type, that is an inbuilt function in deep learning. It is an inbuilt function in this era of memory. If you type with a small m, it is different. If you type with a capital M, that means it is a default model taking the corresponding input as Z and the fake prediction as output. Okay. So we are just saying what we are saying now, sir. What the output also we are declaring on the right hand side. You will get confused. Output will be always there on the right hand side. But we are defining a model. This model will take a noise source as input, and it will produce an output called fake prediction. That's what we are saying. And compiling the model. That's why I keep on telling them we have not run the model. We are just building the model. When we build the model, the syntax is like model followed by input comma. So what is the combined model? Ultimately, one thing I will be very much interested to know, the combined model's output is also equal to 1. That means the combined model is also going to say whether we have generated, whether the generator has, the combined model has taken a normal image or fake image. Those things are. And this is next important module that is taken here, which is called that every run of your combined model to showcase your image and save your image. What is done here now? The images are somewhat rescaled. Here we call it sample underscore images of. Sample underscore images is not an inbuilt Python command. That is what we are declaring here. Define sample underscore images means for every epoch, the particular images that are generated in batches should be saved to your folder, and also they should be plotted. And also some rescaling operation is done here. And next, coming to the important part called training the discriminator and training the combined model. So as you can see here, X-train. What is X-train? X-train is the actual data we are taking. When you go back to the code also, we can infer that the X-train is nothing but the actual data samples we take here. That is nothing but the X-train of index. So index, we are generating some random. So all those things, we go for micro analysis of the code, it is tough to complete this. And after that, we generate some noise, as we have seen here. Some noise is given as input to the combined model. That is what is given here to generate the fake images. So here two things we need to infer. The real images are taken and the fake images are generated. Okay. And the discriminator is trained with both the real images and also with the fake images. Okay. So we are giving the label for real images as 1. We are giving the fake images label as zeros. Okay. And from that we are calculating the discriminator loss and the discriminator accuracy. And then we are averaging the loss and the accuracy. Very things. So first initially we are training the discriminator with real images and fake images with the labels as ones and two. Then training the combined model. That's what when I gave the explanation, first I told the discriminator is first genuinely trained by giving the original samples label as 1 and the fake samples label as 0. Then after some time, this is called as training the combined model. Training the combined model in the sense, in the last function we have this term D of G of Z. That is for the fake samples, for the noise, the generator is generating fake images. That is given by G of Z. And for the fake images, what is the decision of the discriminator? That is D of G of Z. This is the combined model. And the combined model is acting here. So the combined model, what is done in that? Again, noise is being called. For the combined model, you are training on batches with the noise as input, the ones as the. So this is what is very, very important in a GAN, which we will not do in any other machine learning operation. Usually, the original image is given as 0 and the fake images are given as, original image is given as 1 and the fake images are given as 0. But here we are twisting the truth. We are just faking the discriminator by saying noise inputs as 1. So what will happen automatically after some time? The loss of the combined model will be very high. It keeps on being high with the noisy input, fake images taking the label as 1. After some time, the combined model will twist the truth. It will generate the data that are similar to original data so that the lie is being made as a truth. It is the, instead of generating noise, it will start generating the original images so that the loss becomes reduced. So then the mapping will be done to real images, synthetic images that resemble the real images and the label will be equal to. Then in such a situation, the loss will become getting. That is the concept behind your generative accuracy. So finally, we are showing the loss of the generator and discriminator. So combined model loss is very high and discriminator loss is very less. Okay, we are not initially when we are training the discriminator separately, we are giving the proper inputs. That's why the discriminator loss is very less. But combined model less keeps on oscillating. Why? Because you are faking the combined model. You are giving the noise input and drilling it as equal to drilling input, so that the loss gets fluctuated. As you can see, the model has not compiled properly. So once it compiles properly, the GAN outputs, whatever I am able to generate, will be very much resembling the original images. So as far as concerned, you have designed a very much baseline model of your generative adversarial network, which can generate synthetic data that resembles the original data. Finally, when you execute this particular lines, whatever the images that are being generated will be saved in your local environment. You can download that and see what are all the GAN generated. In fact, we trained the GAN on some COVID chest X-ray images also. We got some better inputs. So these are the original COVID chest X-ray images. Whereas these are the GAN generated. So I know there is still a long way to go because here the loss functions are the conventional loss functions we are using. Binary cross entropy we are using, which is nothing but this one. Instead, we have to manually implement this GAN based loss so that the generated images will be somewhat better. I think that is it for this session. And then these are the references. Anything else I want to say now? We have some work. I told some tabular data set. So we have generated tabular GANs also. It's the UG project we have done some couple of years ago. So the National Health Repository of Medicine gives a COVID-19 data set as I told you. We have generated, sorry, the data set consists of 1,604 entities. Using tabular GANs, our students generated around 1,000 data. So the burden of proof is on us. So when we generate synthetic data using GANs, it is our burden to prove that the synthetic data, whatever we generated, is as statistically significant as the original. So the burden of proof is there. So when you read the papers that work on GANs, you can see that some papers they generate synthetic images using GAN, and they will end up saying that when you augment the data, augmentation of data is done using the GAN generated images, then accuracy is there. Likewise, some papers will find. Whereas here, what they have implemented now progressively growing GAN. So this is a progressively growing GAN, which is little complicated in architecture. Whereas baseline for anything is this one. That too, we have not taken the data sets like MNIST. So in fact, the online data set for MNIST is only downloaded, and we kept on changing the code for to work with real time. From our folders, we have to take the input, and we will be able to download the generated images also. It will be useful for publications. Then I told about loss functions. I just wanted to show that how can you generate your own loss functions. If possible, we'll see in some other way. Okay, that's it, sir. My presentation is over. Thank you all for your attention. Do you have any queries? About it?
Dear participants, if you have any kind of queries, you can raise, please. Rajesh sir.
Yes, sir.
It was a great session, na? Almost 1.5 hours without a break. You have taken a nice session, sir.
Sorry, excuse me.
I think someone has opened the mic to throw some question.
I think Saidulo, any question, please?
Yes, sir.
Yes, you can go ahead, please.
Good afternoon, sir. Saidulu.
Yeah, good afternoon.
How does a CNN differ from a fully connected? How does a CNN differ from a fully connected neural network?
Yeah, neural network consists of limited number of layers that connects to machine learning. So, from my understanding, this is
Find your mentors.
it's not a textbook matter I am telling, but from our understanding, if we connect, the artificial neural networks are more connected to machine learning, having less number of layers. And if you operate with more number of images, thousands and millions, thousands and 10,000s of images. So that connects to deep learning that has to be done with the convolutional neural network. Importantly, you have something called as a convolutional layer in C. Whereas artificial neural network is little different, where you have a very standard type of input data. Features are extracted by domain-specific methods. For example, you want to extract some type of features from images. Now you will extract like energy, entropy, or wavelet-based values you can extract, and those numbers will be fed as input to the neural networks. And directly, immediately after the feature extraction, the classification or learning or weight learning will happen. Whereas in deep learning, we have convolutional layers explicitly for this. So one more perspective we can say is domain-specific feature extraction is more in machine learning, whereas in deep learning, same convolutional layers, same type of activation functions, but it is successful to any domain. That is what is the advantage of your decisions. Thank you.
Thank you. Thank you, sir.
Thank you, sir.
Yes, ma'am. Thank you. And I thank Dr. Ravichandra.
Thank you, sir, for your valuable time and accepting as a resource person, sir. Your presentation has provided lot of information and insights of AI in medicine and detailed explanation of data sets and various types of CNN, ANN, and how it is working. Thank you, sir.
Thank you, ma'am. Thank you. Shall I leave?
Yes, sir. Yes, sir.
Thank you. Thank you so much.
Thank you so much, sir.